Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with lesson number 7 in our incredible new tutorial series where you are going to teach the robots who's going to be the boss. I'm going to need you to pour yourself a nice big mug of iced coffee. That would be strong black coffee poured over ice, no sugar or sweeteners, none are needed. I am also going to need you to get out your robotic gear. What? You don't have your gear yet? Look in the description down below. There is a link over to Amazon where you can get your most excellent Elegoo Smart Car 3.0 and you can play along at home. I also need to take a second and, as always, give a shout out to you guys who are helping me out over at Patreon. It is your encouragement and your support that keeps this great content coming. You guys that are not helping out yet, think about looking down in the description. There is a link over to my Patreon account. Think about skedaddling on over there and hooking a brother up. But enough of this shameless self-promotion. Let's talk about what we are going to learn today. And I do believe that if I remember correctly, last week what we had done was we had shown how you could control the speed of the Elegoo Smart Car by doing an analog write to those enable A and enable B channels. If we do an analog write instead of a digital write high, we can control the speed. That is the good news. What is the bad news? When we did that, we broke our functions. Okay, we broke our functions. Before we were changing the speed, we could set the distance that we wanted it to go. It would go that distance. But then when we changed the speed on it, those functions broke. And so what your homework was for this week was to go in and fix your code where you could drive the correct distance kind of independent of what write value or what speed value you wrote to those enable pins. Okay, let's be honest. Who of you all was able to do it? Was anyone able to do it successfully? Okay, how many of you even tried? All right, how many of you even tried? Well, that's okay, because I'm going to show you the solution today. And if you already knew everything about thinking like an engineer, you probably wouldn't need to be taking these lessons. And so what I'm going to show you today is on a problem like that, the hardest part of it is to get your mind around it and to realize while it sounds real complicated, it's really pretty simple, and math is your friend, and you just need kind of an algorithm or a strategy where you do math to solve the problem as opposed to a whole lot of trial and error. So let's go ahead and let's start with where we left off in lesson number 6, and you can do that by coming over to the most excellent www.toptechboy.com, and then you can go over and using the happy little green search bar, you can search on robotic training lesson number 6, and then I had better get out of your way before you all get very angry at me. And you come down here on lesson number 6, you click the two little page icons, you right mouse click and copy, and then you come over to a fresh new Arduino IDE and you paste into there. So now we are starting off where we left off in lesson number 6. And if you remember, what that was doing in lesson number 6 was we were setting a speed. Okay, we were setting a speed. Where is that? Okay, and here we just set it to 255 and 255, the left and the right, and then we set the speed and then we went forward 10. I think when we had done this last time, we had set it at 100 and 100, and then we had told it to go 10, and guess what? It didn't go 10. Why did it not go 10 even though we wanted it to? Because it doesn't do what we want, it does what we tell it to do. And what we had told it was, we had told it that the delay time is the distance that you want to go divided by 2.45, because if we're going full speed, we were going roughly 2.45 feet per second, and then we delay for that long, and at full speed you'll go 10 feet. But what is the problem? If you're not going 10 feet because you change the speed, I mean, if you're not going full speed, then because you change the speed here, then this equation becomes broken, because by changing the speed, this is no longer the right number, and if this is not the right number, then you're not going to get the right t, and if you don't get the right t, delaying t is not going to have you go the right distance. So this is how I would do it. Okay, I would do it very simply. I would calibrate the car for what speed is it going at the very fastest speed when you write 255, 255, and then what was the slowest speed that we could do and the motor still run reliably, 100. And so how fast is it going when you do a set speed of 100, 100, and how fast is it going when you do a set speed of 255, 255. And I'm not going to do all the values in between there. I'm going to assume that it's linear. So if we do two calibrations in an equation, we should start getting pretty darn close. So let's go ahead and let's do that calibration. Let's start by downloading this program, because we're going to be in a world of hurt. We will be in a world of hurt if we are not running the right program. But I'm going to start by calibrating it at full speed, which is 255 and 255. And remember, last time that we did this, we got a speed of about 2.45 feet per second. I want to redo that, because I want to see, has it changed? Is the car day to day pretty consistent, or is there some variability there? So I'm going to do that, and then after that we're going to come back and do it at 100, 100, and then we will have two different speeds for two different right values. So I'm going to download this at 255, 255. My car is off. It looks pretty happy. Boom. I'm going to take this off. I'm going to switch to the most excellent RoboCam, where you can see our training and test track over there. So I will hop on over there and we will see what this does. I will take my trusty clipboard and we will see here. I am setting it on the starting line. Okay, I'm going to go ahead and turn it on. Okay. And I will set it down on the starting line. And now I'm going to hit the reset, and we're going to see how far this goes. And remember, this was okay, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's changed a little bit since last time, I believe. So I really think we need to recalibrate it. We really need to do a recalibration, because it didn't work exactly like we expected at 10. So things have changed a little bit. So what I am going to do is I'm going to come and I'm going to plug it in, and we will do a calibration. Now remember, we had that calibration function here, which was calf for calibrate forward. And let's see where that was. Our calibrate forward here, and we just let it run for 5 seconds and we see how far it goes. Okay, so we're going to go 5 seconds and we're going to see how far it goes. So I will just do a cal F here, cal forward, and we're at full speed. I'm going to do a cal forward. I think that was an uppercase F. And then we're going to figure out how fast is it going. Hopefully you remember this. I think it was lesson number 5 that we did this in. It is off. Okay, that looks happy. And we're going to see in 5 seconds how far it goes. So the distance is equal to rate times time. Rate is distance over time. And so the distance that we measure divided by the time will give us the rate for full speed. Okay, we are set. I'm going to turn it on. Okay. I'm going to set it at the starting line, and off it goes. 1, 2, 3, Wow, that was a long way. Okay, it went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 feet 4 inches. I'm going to try that again just to make sure. But it went 11 feet 4 inches. I'm just going to try it one more time. I want to make sure that I'm getting it straight. 11 feet 4 inches. I want to make sure I counted right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 feet 4 inches. All right. So, in 5 seconds, I went 11 feet 4 inches. And so let's write this down over here. Okay. And what we will call this is, let me make sure you can see what I am doing. Okay. We will call this, let me find my pen. That looks like a good pen. We'll call this Cal 1. And in 5 seconds, I went 11 feet 4 inches. Okay, now we're going to come and we're going to do Cal 2. And for Cal 2, we will change the speed. Okay, and remember the slowest that we could operate at was 100 and 100. So now I've got the information to calculate what full speed is at 255. Now I need to figure out what the speed is when we are at 100. And if you watch lesson number 5, this should sort of make sense. Car is off. And let's let you look at the car just so you're always kind of seeing what I am seeing. I think like that. Okay, so we set it at 100 and we're going to download that. That looks good. Okay, so again, it's still going to be at 5 seconds, but how far will it go? How far will it go? All right, that looks good. Let's unplug it and let's go let it run. We are on the starting line. We have turned the car on. Okay, and so right exactly on the starting line, hit the reset, and she is off to the races. 1, 2, 3, 4, 5. Okay, so this is 1, 2, 3, 4, 5 feet. That's 5 feet 6 inches. 5 feet 6 inches. Okay. Going to turn it off. So that was 5 feet 6 inches. All right. So I think now we're going to do some math. All right. So I will need to move this. And then Cal 2, what we found was in 5 seconds, it went 5 feet 6 inches. The first thing I need to do is convert these distances into decimal, because you don't want to ever work in feet and inches. You always want to work in decimal. And so 4 inches is a 4 inches is a third of a foot, right? So we have 4 divided by 12 is 0.33. So this total distance that it went here was 11.33 feet in 5 seconds. Okay, then over here, 6 out of 12 is a half, and so we know that here we went 5.5 feet in 5 seconds. Now what do we know? We know that distance is equal to rate times time. But what I want to do is I want to figure out the rate. And so I divide both sides by time. Divide both sides by time. And then time over time makes 1. So I'm left over here with R. Time over time makes 1. I'm left with R, and it is equal to D divided by T. Okay, so this rate is going to be D, which is 11.33 feet, and I should probably put the feet there, divided by time, which is 5 seconds. 5 seconds. So I have 11.33 divided by 5, and that is going to be a speed of 2.26. So the rate is equal to 2.26 feet per second. Now let's look what we got last time. Okay, that seems like not exactly what we got when we calibrated it the first time. Okay, when we calibrated it the first time, it was 2.45 feet per second, and so this time it's not going quite as fast. It's like 10% slower than it was before. Now this is showing a little hint of a problem with the strategy that we're taking, and that is when we're using dead reckoning, if there's variability time to time, you calibrate it and then it might not work exactly the same. What I would suspect is maybe as the battery goes down, full speed starts getting slower and slower, and I've been playing around. This is video number 3 that I've made today, and so this thing could be slowing down a little bit, but that doesn't stop us. That just makes us see that when we're working with something like this and we're using just dead reckoning, you know, just basically open loop control, you're not going to have it always do everything perfect, but we're going to do the best we can given what we have to work with. So over here now we got to do this calibration 2 calculation, and same thing, we know rate is going to be equal to distance over time. Okay, and so the rate here is going to be equal to, what did we say? Did I lose my notebook? We said 5 foot 6 inches. Oh, okay, there it is. Yeah, 5.5. Distance is 5.5 over 5 seconds. And so the rate is going to be, I should do that in my head, but I don't do head math on videos live. And so as I expected, it is 1.1 foot per second. Okay, like that. And so I've got this rate and I've got this rate. All right, and now I think I need to let you go to full screen here. There you go. So now you can see that. All right, now this is kind of the strategy that I'm going to take. I could go in now and calibrate it for a right value of 101, a right value of 102, 103. For every number between 100 and 255, I could go calibrate and find the speed. But I'm going to make an assumption, and the assumption should be a pretty good one. Okay, and so let's try to draw a graph here. This is our velocity or our rate, and this was that right value, right? We had 2 right values. We did a right value of 100, and then this would be 150, 200, 250, and then we did a right value of 255. And at a right value of 100, we went 1.1 feet per second, and at a right value of 255, we went 1, 2 and a quarter, like right there. All right, so what we're going to assume is we're going to assume that the function is linear between there. And so if I can calculate the equation of this line, which I think I can, if we can calculate the equation of this line, then for any velocity, for any right value that we put in, we should be able to calculate the car velocity. For any right value that we put in, we should be able to calculate the car velocity. And then what we would do is, instead of just putting 2.45 here, we would put our calculated velocity that's based on what that right value is that we did, right? That 100 or that 150 or that 255 or whatever. Is this strategy making sense to you? I think it's kind of something, I think that it should work. Okay, but what we need to do is we need to kind of see what these 2 points are. Right? We need to see what these 2 points are. And so this point has an x value of 100 and it has a y value of 1.1. So if I apply a right value of 1.1, I end up, if I apply a right value of 100, I end up going 1.1 feet per second. Now this point, if I apply a right value of 255, then I end up going 2.26 feet per second. Now I have 2 points. Okay, and those are very important. This is point 1 and this is point 2. All right, now we will come over here and we need to write the equation for that line. Well, what do I know about a line? Well, the first thing I know is y minus y1 is equal to m onto x minus x1. Okay, and hopefully you guys have at least seen this before, and at least it's kind of ringing a bell. And we know that m is equal to y2 minus y1 over x2 minus x1. All right, now we're going to be good engineers, and we're going to see we're not really dealing with y and x. We are dealing with velocity is our y and right value is our x. And so let's rewrite this in terms of the variables that we are using. So we're still going to have a slope. That slope m is going to be equal to the velocity 2 minus velocity 1, because that was our y value, over right value 2 minus right value 1. Okay, now let's calculate our slope. M is equal to, well, I've got the velocity 2 is 2.26 minus 1.1. So the numerator is going to be the velocity 2, 2.26 minus velocity 1, which was 1.1, over right value 2, which was 255, minus right value 1, which was 100. Okay, and you guys, when you put this in your calculator, make sure that you use your parentheses. Okay, because if you don't use your parentheses, you're going to get wrong answers. And guys, the big, huge mistakes I see is not using your parentheses and inappropriate use of parentheses and getting mistakes. So I'm going to come in here now and I'm going to say 2.26 minus 1.1 divided by, and then an open parentheses, 255 minus 100, close parentheses, equal, and I get a slope of 2.25. Now you might get a slope slightly different because your car might not work exactly like mine. Okay, but that is a very important number there, because that is what we're going to use now to get the equation of our line. So now let's go in, and remember y minus y1 is m onto x minus x1, but we need to now again not use y but use the variables that we're using. For us, y was v for velocity, so I'm going to have v minus v1 is equal to m, which I know now is 2.25 onto x minus x1, which is going to be right value. So that's going to be right value minus right value 1. Now I can use either this point or I can use this point. I think I will use this point for my calculation. Either one will give you the exact same answer. But I'm going to have velocity minus velocity 1, which is 1.1, is equal to 2.25 onto right value minus right value 1. What is right value 1? It's 100. Okay, so that is going to be 100. Now I need to distribute the 2.25, so I'm going to have V minus 1.1 is equal to 2.25 times right value, okay, minus 100 times 2.25, which I can do that in my head is 225. All right. Now I need to add 1.1 to both sides, so I have V is going to be equal to 2.25 times the right value minus, okay, and I would take 225 and I'm adding 1.1 to it, so I have a minus 225, and then I'm going to add 1.1 because to get it off the other side of the equation you add 1.1 to both sides, and I end up with minus 223.9. Okay, minus 223.9. So this is my equation of my line. Now this is a little math tip. Anytime you do this, go back and put one of your two values in and then see if it works for that, and that will tell you if you did the equation right. Okay, that will tell you if you did the equation right. And so let's go in and let's put in this value and let's see if we get the right thing. So I'm going to put in 255 for right value, so I'm going to say 2.25 times 255 minus 223.9, and I get a crazy wrong answer. Let me try that again. Where do we make a... We made a mistake in here somewhere. Let's see. So let's make sure that we did this right. So let's come up here and look. We have M is velocity 2 minus velocity 1. That's right. Okay. 255 minus 100. That's right. And V minus velocity 1 is 2.25 times right value. Well, let me see again. 2.25 times 100 equal 225 minus 223.9. Got 1.1. Okay, let me try 255 this time. So I'm going to have 2.25 times 255 minus 223.9. And man, I'm getting a crazy wrong answer there. Okay, let's see if we did the calculation of the slope right. 2.26 minus 1.1, enter, that is right. And then divided by 255 minus 100 with parentheses, and that is not 2.25. How did I get that slope so wrong? Okay guys, I did a calculator mistake there, so let's get this and let's erase. It is right above that, and let's start over. And why do I not edit out these mistakes? Because everybody makes mistakes and I want you to see how to recover from them. Okay, and so this M, let me put my step in, M is equal to 2.26 minus 1.1 would be 1.16 divided by 255 minus 100 would be 155. And so I got a crazy wrong slope last time. M is equal to 1.16 divided by 155 is going to be 0.0075. And so this is 0.0075. Now yours is not going to be exactly that, but it should be very, very close. Okay, it should be a small number like that. Now we're going to do this equation of the line again. V minus V1 is equal to M on to right value minus right value 1. And so we have V minus 1.1 is equal to 0.0075 times right value minus right value 1, which is 100. Okay, and now we need to distribute that 0.0075, so I'm going to have V is minus 1.1 is equal to 0.0075 times right value minus 100 times 0.0075 is going to be 0.75. All right, now I need to add 1.1 to both sides, so I'm going to have V is equal to 0.0075 times right value, and then minus, let's see, that's a negative 0.75. I add 1.1 to both sides, so I say plus 1.1, and I end up adding 0.35. And so this is going to end up being plus 0.35. Okay, so why is this important? Let's not lose track of what we are doing. Okay, this means that we can come in and we can put in a right value that would be like 100, or that would be like 255 or 175, and then it will calculate the velocity of the car for us. So this is something that we're writing in the program, the right value, and then this is telling us what the expected velocity would be. Now I'm going to check this just to make sure that this equation is right. So if I put 0.0075 times, let's do the 100, okay, and then plus 0.35, I end up with 1.1. Okay, and 1.1 is what we had wanted to get. So that's just saying that this equation is right. All right, so what this means is we can come over now and we can adjust our program where we just don't dumbly type in a velocity. We don't just dumbly type in a velocity. We use a calculated velocity depending on what right value we sent to the car. Okay, so it's not always going to be 2.45 here, right? It is going to be velocity. Okay, and then what is velocity going to be? Velocity, and I'm going to move this where you can see the velocity equation, right? Okay, it's T is equal to D, the distance divided by velocity times 1,000, and that 1,000 is to convert from milliseconds to seconds, all right? And so now, or from seconds to milliseconds, so now what we're going to say is V is equal to 0.0075 times right value plus 0.35. Now, what do we need to do? Now you can see I got the equation in there. I'll move this back down now because we got the equation in there. What's a couple of problems? Well, this was supposed to be plus 0.35. One problem is if we're going to use V, we've got to declare it. And so here we're going to make a float of V just so it's been declared down here and the program doesn't gripe at us. And then we need right value. Well, what's the right value? Well, the right value is set up here, right? There's like a left right value and a right value. So we need to pass those in. But let's just say for now that, let's just set it as right value. Speed. Okay, what we'll say is if the left is 100 and the right is 100, then we'll just create one right value, which is equal to, you know, whichever one. You see, I'm kind of, okay, this is what I'm going to do. Later on, we're going to want to give it different speeds, but what I'm going to say is there's a right value that I'm going to spin. Let's call it a speed. I'll just call it right value. WV for right value, and that's equal to 100. And for right now, okay, we're going to make left equal to the right value and right equal to the right value. And it's unfortunate that there's right, like right hand, left hand, and then there's right, like you right. So these are two different rights that we're talking about. So we're going to set the right value to 100. And now we set speed with the left and the right, which it should know. And now when we come down to calling our forward, we've got to pass it not just D, but we've also got to pass it float. This would actually be an int right value. Okay, so now this forward is going to know what right value is. It can then calculate velocity, and I better bring this in as a float. Okay, because sometimes you get goofed up if you're doing integers and floats at the same time. I wouldn't want this to make that 0 when you divided. Okay, so now you set right value up here, and then when you come down, you pass forward right value. You calculate the velocity, okay, and then you delay that long, and then it should go that far. All right. I think we should probably go ahead and fix backwards at the same time. And so on backwards, we need to send it float right value as well. And then these 4 lines of code are going to be exactly the same for the backwards. Okay, and those would just replace that. All right, so now if this works right, now I should have fixed. Okay, so we're still going to set the speed here. Okay, we're still going to set the speed, but now instead of calling F, which was my calibration F, we're just going to go forward. Okay, and then we need to send it. How far forward do we want to go? I want to go 6 feet. Okay, and then I need to send it the right value so it knows what speed I'm going to end up with, right? So if I send it right value, it will know how fast the car is going. So if I do this, then I should have hopefully fixed, hopefully that will fix our distance problem. So let me plug this back in. And then it should go the right distance no matter what the speed is, okay? And so now we are going to download this. The car has been off. Whoa, right value. Oh, okay, I think down here in the backwards we didn't declare right value, so I got to say float right value. We passed it. Oh, wait a minute, we did. I'm sorry. That does declare it there. It was up at the very top. We didn't say int right value. Okay, so then when it sees the right value here, it will be okay, and we do need a semicolon or a colon there as well. All right, so now let's try it. And we did not put our semicolon there. Again, all this time I'm spending on Python is making me forget to do those things. And so that was in forward, so it's probably wrong in backwards as well since we copied and pasted. Now let's give it a try. It's going to work this. Ooh, V was the right value was not declared here. What do you mean it was not declared? It says V. Oh, that's the one I should have done. This is backwards, and I copied and pasted, but I didn't put up here float V because we're just using V the first time here, so you've got to declare it in your scope. Okay, and so now we have said that going at 100, a speed of 100, we want to go 6 feet. And so I'm going to unplug this. I'm going to turn the car on. We're going to see how well we do. And we need to go to the most exceptional RoboCam view. We are on the starting line. We are on the starting line. We are going to hit reset. I hope this works. There it goes. 1, 2, 3, 4, 5. Oh, okay. It's like 1 inch short of 6 feet. It is 1 inch short of 6 feet. So that was pretty darn good. Let's try it again. Okay. Let's try it again. There it goes. 1, 2, 3, 4, 5. And again, it's about 1 inch short of 6 feet. What does that mean? That means the calibration is not perfect. Okay. The calibration is not perfect. All right. But now let's go up to 255, and let's say that I want to go 8 feet. All right. And so let's download that into it. 255, I want to go 8 feet. Okay. And so here we are going to download it. So you see, I'm changing the speed and I'm changing the distance. Is it going to get it right? Okay. So we will come and we will try again here. We're hoping for 8 feet. We are thinking like engineers. We are acting like engineers, and we're still frightened. We're very frightened. But here we go. 1, 2, 3, 4, 5, 6, 7, 8. Oh man, it nailed it. It nailed it to the inch. So at the high end, it's really accurate. At the low end, not exactly. Well, let's try an intermediate one. Let's say that we're going to go 175. Okay, let me show you back over here what we're doing. So this time we are going to go at a right value of 175, and I want to go, let's go for it, man. You see, it works, and then I get overconfident. We're going to try to go 12 feet. Throw caution to the wind. We're going to try to go 12 feet, okay? And so we will need to download this. Changing it on the screen does not change it in the smart car. Okay, and let me turn this off. And now we are going to download it. Okay, and now I will unplug it and we will go to the RoboCam. I got to let it finish its first little cycle there. Okay. And now I've got it all lined up. Ready, set, go. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think we went too far, if I counted right. Let me try again. You notice how this thing is going a little bit to the left, which concerns me somewhat. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So we wanted it to go 12 feet. We wanted it to go 12 feet, and it went 13 feet. Okay. But you see, this is kind of okay. because what we know is we know that this function might not be exactly linear. Okay, we assume that it's linear, but maybe it's not exactly linear. And the thing is that it's going to be pretty close most of the time. So what's the difference between 12 feet and 13 feet? That's 10%. And so if we're sitting here and running this car autonomously and we're getting within 10% of the target, that is pretty darn good. Now, the one thing that did concern me a little bit, it was really listing to the left, that when we got out there that far, it had kind of veered off to the left. And so I want to make sure that we are in fact, how do we come back here? Let's come here, and let's go there, and then let's come here. Let's make sure that I didn't make a mistake here, that I'm sending right value is 175, then I'm setting left to 175, I'm setting right to 175, I'm passing left and right to set speed, and if I come down to set speed, I am sending left val to our enable A, and I'm sending right val to enable B, and I'm getting left val and right val. So that looks right, but it's just as I'm going a long distance, it's kind of like the wheels on the right are running a little bit faster than the wheels on the left. And again, this is just showing you one of the limitations of trying to do dead reckoning. When you're doing dead reckoning, it's just not going to work absolutely perfectly. Okay, so how would you take this to the next level? Well, what you would do is you would probably put on here a compass, and instead of saying go, in a open loop fashion, you would continue to head north, and if you see that you're coming off of north, you would speed up that little motor a little bit until you were going exactly the direction that you wanted to go. And if you guys are up for it, later on in later lessons, we can start trying to do some closed loop control of this thing. We'll have to buy some more components to do that, but I want to do as much as I can without having to buy anything else for this. But that's kind of like there's going to reach the point that we can't do any better with the hardware that's on here. But we're learning a lot, right? We learned some really, really good math today. I think I want to do one more. Let's say that I want to go, 100, and let's say that I want to go 4 feet. Okay, so I'm going to go forward 4 feet at a slow speed of 100. So let's come back over here to the overhead cam, and let's plug it in. Just kind of play around with it with different values and see what happens. Okay, so I'm going to unplug it, and I'm going to go try this out, and we will go back to the RoboCam. Okay, so we're going to be going slow, and we're going to hope for 4 feet. Hit reset, and we go 1, 2, 3, 4. Bam! Nailed it. Nailed it absolutely to the inch. I'm going to try that 175 again. I'm going to try that 175 and see how it does at 4 feet. So let's come over here. And let's set that speed to 175. And I have to make sure that you can see what I'm doing. So we're going to go 175 for the right value. And we are going to go 4 feet. And we are going to plug it in. And we are going to download it. And there it goes. So 175 is pretty good, and we're going to tell it to go 4 feet. We are on our starting mark. We are hitting reset. And we're off. 1, 2, 3, 4. Okay, man, that 175, it is just not calibrated terribly well. It's about 3 inches past it. And so let me see the 255. because what I'm kind of looking at here is I'm looking at linearity, okay? And so it worked perfectly at the 100. And now let me go up to the 255. And then let me download that. And that's a goal of going 4. We are on our starting marks. Okay. And then we are hitting reset. 1, 2, 3, 4. Dead on. Absolutely dead on. Okay. Absolutely dead on. So what does this mean if it's absolutely perfectly on the end point? Okay, so let's look at kind of like our actual here. Okay, let's look at our actual here. What I find is, let's see, there it is that if I go 100, a right value of 100, it works perfectly. If I do a right value of 255, it works perfectly. But in between at 175, it's going a little bit faster than what the linear is. And so what that means is, that means that this curve is not perfectly linear. Man, I drew that horribly. That was terrible. What that means is, let me see if I can put it here. Okay. It is very hard to draw with this tablet. Okay. What that means is we're assuming that between here and here, between those two right values, we're assuming that it's linear. But really what we found is at 175 it was going faster than what we thought. And so we can see that it's a little bit of a parabola. It's probably something a little bit more like that. So what could we do? We could go in and we could do more points, and we could figure out what it is, and then we could fit it to something that's not a straight line. We could fit the little bit of curvature in there, and we could try to calibrate it better. But really, I'm not going to do that because there's enough variability already that you would be doing a whole lot more work, but you wouldn't get a whole lot more accuracy. Because I think what is going to happen is, is that these two endpoints, if the battery is fully charged, it's going to be going a little bit faster, and as the battery runs down, it's going to be going a little bit slower. And the same thing down here, it's going to be faster with a full charge and slower with a lesser charge. And so I think that you can see that there is going to be a range and an uncertainty in here because of the battery. All right. And so when we're doing this dead reckoning, there's only so much accuracy that we're going to get. I will say though that given that this is an inexpensive robot car, and the fact that we don't have any feedback, it doesn't have any way itself to know how fast it's really going, I am really pleased with the accuracy that we are getting. I mean, I think that this is enough to play around with and to program it and to have fun. Okay, now let's talk about the homework for next week. This worked great. Okay, this worked great, but this is the kind of strange thing, that what the user inputs is he inputs 255 or 125. That's a completely meaningless and arbitrary number. What I want you to do is go modify the equation where you input your input, and it would help if you could see, and it would help if I could find my cursor. Right, there it is. That what you're going to do is you are going to input not an arbitrary meaningless number of 100 to 255. You are going to input a number, and let's say you go from 1 foot per second to 2 feet per second. Okay, so you're going to input these as your inputs, and then what you're going to have to do is from that is your desired velocity. So you're inputting something that really makes sense in the physical world. You're going to say, this is how fast I want the car to go. Okay, and then you're going to have to go from that to you're going to have to calculate the right value. So rather than just throwing out a right value that you don't have any idea how fast it's going to make the car go, you are going to put in a value between 1 and 2 feet per second, and then you're going to calculate the right value, and then you're going to go that fast. And still, when you do this, don't break your distance thing. And I'll give you a hint, it's really pretty easy because you already have this equation which relates the velocity to the right value. But right now it's set up to where you pick the right value and you calculate the velocity. Well, what I want you to do is input the velocity and calculate the right value. So again, this is going to be some algebra, but then the person could say go 1 foot per second for 10 feet, turn around, go 2 feet per second for 3 feet. Okay, you can give it parameters that make a lot of sense in the real world. Hey, I am loving this. I'm loving this because we're doing complicated things that this inexpensive car is really allowing us to do pretty good. And I kind of compare this to the Lego Mindstream or Mindstorm or whatever that was. It was some robotic kit that I got for, it was like $250 or something like that. But you got that little car and you told it to go straight, and it's like the wheels weren't round and it went ka-chunk, 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 ka-chunk. And it was like you couldn't make the thing go straight. It was just really arcing. I couldn't get that thing to ever do anything meaningful because mechanically it was just so unstable and so not rugged. For a car, for a little robot that's under $100, I am really thinking that this is really doing very well, and so I'm having a lot of fun with it. So we're going to continue doing projects that don't require you to buy any more hardware, but there will probably, so be putting your little coins away, there will be probably kind of like one thing I would like to do is, in fact, give me feedback about what you would like to see. But let me give you just a couple of ideas. Hold on just a second. I will be right back. I am looking for okay, so eventually, where would I like to go with this project? Now, don't get mad at me because I'm saying we're going to have lots and lots and lots of lessons with exactly the hardware that we have here. Exactly the hardware we have here. We're going to have lots and lots and lots of lessons. But I'm always thinking like 25, 30, 40 lessons ahead. And so what I think would be really neat would be if we put a compass on here, a digital compass, and have that compass work with the Arduino where you give it a direction to go and it goes that direction, but it's not just guessing the direction, it knows the direction because it knows where it's heading. So I say go 15 degrees east of north, and then that compass is going to tell it whether it is going that direction or not. And then the motors would adjust a little bit. You'd have a little control system to where the speed of the motors would adjust to keep it going that direction. I think that that would be really, really cool. Another thing that I would think would be really, really cool, I don't know, you guys have probably heard of the Raspberry Pi. Well, there is something called the Raspberry Pi Zero, and this is a Raspberry Pi Zero, and it costs $10, and it will run Linux. And what I am thinking is a Raspberry Pi is like an Arduino on steroids, And so it is hard for the Arduino to talk back to us. I mean, I know there's that Bluetooth module, but there's only so much we're going to be able to do with Bluetooth. What I'm thinking would be cool would be to put the Raspberry Pi on there. And in fact, this is a Raspberry Pi Zero with a cool little case, and it has a camera in it. Well, what if instead of this ultrasonic sensor, what if we put the Raspberry Pi with the camera on here, and the Raspberry Pi has Wi-Fi, and we could be sending back to our home-based computer live video. And then what if we drove this thing from our home base, kind of like a first-person view, like we were really sitting in the car driving it. So we would be driving it, but we could see where we were going and what was in front of us. And since the Raspberry Pi has Wi-Fi, this could kind of go anywhere, you know, in your range, within the range of your Wi-Fi. I think that would be pretty cool, and that wouldn't be that hard, and these little Raspberry Pi Zeros don't cost very much. So those are kind of like two different directions that I'm thinking after we've exhausted our existing hardware, would be to get a Pi Zero with a camera. That wouldn't cost much. Also to get the little compass, the little electronic compass module, where we could be heading, instead of just kind of going in a guessing direction based on where we think we're going, to actually set the direction and constantly monitor it. And that way, if the car is starting to veer to the left, it would see that and it would correct itself. Let me know if those two ideas sound interesting. Also, let me know if, you know, man, if you have to get more hardware, you're just absolutely going to have to drop out. You know, kind of like, let me know where you are as far as these things go. But I promise you, we're going to have lots and lots and lots of lessons, lots and lots and lots of learning with just the hardware that we have here. Also, we're going to continue to do the math. I'm going to continue to teach you to think like an engineer. And what I need you to do is really understand how to do a line. If you could not follow what we did here, hop on over to the Khan Academy and look in those algebra lessons. The Khan Academy is free. Look in the algebra lessons and watch the couple of videos that he has on lines, understanding linear equations. And it's probably like 5-10 minutes of video. Watch a couple of videos on lines and make sure that you understand what I'm doing here, because so much, believe me, so much of engineering is just understanding a line. And I think you maybe begin to see today some of the power of doing that. All right, guys, man, I hope you're having as much fun taking these lessons as I'm having making them. I'm loving this. I'm eating it up. I'm loving my little Elegoo Smart Car. And so you guys tune in next week and really try to do that homework. And then what I will do next week is I will go through the homework and show you what my solution is. So this is Paul McWhorter from TopTechBoy.com. Be sure to give us a thumbs up. Be sure to subscribe to the channel, ring the bell, share this video with some other people. Let's see if we can develop some momentum behind this robotics business. Paul McWhorter, TopTechBoy.com. I will talk to you guys later.